So there are two different types of circuit configurations for this class. There's a series circuit and a parallel circuit. Today's set of notes, we're going to look at the series circuit, where the components are connected end to end, and there's only a single path of the current to flow. Kirchhoff's laws, he's got a voltage law saying the sum of all the voltage drops in a series circuit equals the total applied voltage. So if we look at this series circuit, it's a path is open anywhere, the current will stop flowing to all the components. So if we take off this second light bulb and we move it out here, it's not a continuous path, so the power is going to go out. So if we look at this, there's a lot going on in this screen, but there's a couple things you should be able to take out of it. One, you should be able to look at what a series circuit looks like. You should be able to look at it and go, that's a series circuit. With that, then, you should be able to then know and use your formula sheet that the total resistance equals the sum of all the resistors, so 220, 470, 1.2 thousand, and that the sum of the voltage, that total voltage of 12, is equal to the voltage here plus the voltage there plus the voltage there. So series circuit, current is going to stay the same. We're going to have some voltage drops. So we're going to take this and we're going to do some calculations with it. We have a battery source or power source of 12 volts. There's at the first resistor. At the first resistor, there is a current and a voltage. At the second resistor, it has its own voltage, it has its own current, and at the third resistor, it has its own voltage and current. We can go ahead and calculate all those. So we've got a series circuit, so we're going to calculate the resistance first because we have those three together. So we're going to take the sum of all of those, add them together, and we get 1.9 kilo ohms or 1900 ohms. We're going to then calculate the current. Well, now that we have the total resistance and the total voltage, since V equals IR, I equals V over R. So we're going to take 12 divided by that 1900. Pay attention to your units as you're working through that. Move that decimal place 3 times. We've got 6.3 milliamps. So the total current is 6.3 milliamps. And since this is a series circuit, the current here is 6.3, 6.3, and 6.3. So what does that mean? That means we can go ahead and calculate the voltage at each one of these components. So voltage is equal to current times resistance. So we know the current at resistor 1 is 6.3 milliamps. We know that the resistance is 220. Move the decimal place 3 times, go back to the base unit, multiply the 2, we get 1.397 volts. Do the same thing at resistor 2. Same current, different resistance, multiply those two. Turn back to the base unit, we get 2.84984, and same thing at the third resistor. Same current, new resistance, go back to your base unit, multiply those two out. We've got the resistance across that component or that voltage drop being 7.619. How do we know if those three numbers are correct? We go ahead and look at the voltage law. Voltage at 1 plus 2 plus 3 should equal 12. Take the 3 answers from the previous page, add those together. We've got 12 volts total for that circuit.